In this video, I'm going to show that the Poisson distribution is an example of an exponential family distribution, which we use in general linear models. So when you're doing a general linear model, you need for your response variable y to come from this exponential family distribution. You also need to specify the length function, which we'll talk about later in this playlist of generalized linear models. Okay, but right now, focusing on the distribution of y, y must have be from the exponential family distributions, which take this form. Okay, so this is the general form. Examples include the Poisson, the normal, the gamma, the inverse Gaussian, the binomial. And so in this video, we're just going to show that the Poisson is of this form. Okay, so how do we do that? Let's start with what the Poisson distribution looks like. Right now, I'm just going to write theta and phi. But Poisson distribution generally is written as e to the power of negative mu. So I'm going to need to figure out what mu is with regards to theta and phi. And then mu to the power of y divided by y factorial. Okay, so this is what the Poisson distribution function looks like. So how do I make it look like this? First thing is I need to use this little trick where e to the log of something is just that thing, right? So e and log cancel each other. So let's do that. Okay, so I'll have e to the log of this stuff here. Mu to the power of y, y factorial. Okay, now I'm going to use my property of log, and I have a division sign there, which is just going to become a minus. Okay, e to the power of log. So I have mu to the power of y minus log of y factorial. Okay, let me close off that parenthesis. And when you have two exponentials that are multiplied by each other, you can write that as the sum of those exponentials. Okay. Lastly, that power can come down using my properties of logs. Okay, and now I'm almost there. Okay, so now I just kind of have to figure out how do I make it look like that exponential family distribution? Well, I need y times theta. Let's see, I do have y times something. I have y times the log of mu. So actually, let's go ahead and do that. Let's say theta is log of mu. Then if I look for phi, I'm looking for something divided by. I don't have anything divided by there, so I can actually just go ahead and say phi is equal to 1, because anything divided by 1 is just itself. So let's go ahead and plug this in. Let's go ahead and put this in the front. So I have y times theta, right? Because I'm trying to make it look like this here. Minus, instead of minus u, let's plug in. So if theta equals log of mu, then e of theta is equal to u of mu. Okay. Then what else do I have? So that was these two, and then I still have this minus log of y factorial hanging out in the back. All right. So now I can go ahead and say what a of phi is just going to be 1, right? Because I don't have any denominator there. B of theta is this term right here, e to the power of theta. And then c of y and phi is just going to be this negative log of y factorial. Okay? And so there you go. This is the Poisson distribution. And these are your functions for A, B, and C written as an exponential family distribution. Okay, and these are helpful later if you want to find, for example, the variance or the expected value of y. You can use these functions and then properties of the exponential family distribution to kind of quickly arrive at your answer.